Hi everyone, today I would like to go over the changes I made in my project since the last time I posted on my channel. Some of these changes were significant, some of them are quite more decorative rather than functional. I changed the microcontroller to a more well-known platform, that is the AVR. It is made by the same company as the previous microcontroller I used, the PIC or the PIC, but this one has excellent documentation and it's somewhat well known in the community, so that makes my job easier. I also swapped the package for one that instead of having two rows has it's four-sided, the QFN, I think. Yeah, the TQFP. That gives me around, I think, 4 additional pins that I can use instead of, because it's 32 instead of 28. There is also a new programming interface that I have to get around. It's quite a shame because I have already purchased a special tool that is used in programming PIC microcontrollers. The PIC kit. I mean, it works, but right now I don't have any use for it. So that's the most significant change I have made, at least for maybe it's not. I'll show you later what other changes I have made. Here nothing's changed. I repositioned some stuff on the schematic itself. Here's nothing. This is the most important issue that I'm facing right now. It's the issue I'm facing is if this circuit is proper or not, because right now the circuit is supposed to work to use all of the features the TL494 provides, but I'm not sure, because at the same time this is quite I don't have anyone else using it in such a way, so I will have to verify if my way of thought is correct, and if I when I will be ordering this PCB, if I will not be just ordering an expensive piece of junk that I won't be able to use. So this is something that I need to check in a more controlled environment. Here I changed the diodes. I'm using now more powerful diodes. Instead of 5 diodes, now they are only 3, although they are in double packages, so that's kind of, so maybe it's 6 instead of 10. They have similar voltage drops to the ones I used previously, so that significantly increases the efficiency, since now it's 2 voltage drops instead of 3 voltage drops, which drastically, like around 10%, maybe 5. I didn't make any precise calculations regarding this change yet. Here is kind of unusual circuitry. It's a bootstrap circuit, since I wanted this N-channel MOSFET to work on the high side, and yet these, like, most people would think that the best way to have some sort of high side switching is for you to just use a P channel instead of N channel, but the problem is that they aren't just widely available. Just N channels are so much often used than the P channels that it's just not worth it for manufacturers to manufacture any sort of high power P channel MOSFETs. So that kind of hinders my progress, but as you can see, I have already dealt with this issue. So now I have this circuit with the bootstrapping capacitors. It's kind of similar to what happens here, but it's like in not in an IC package, so everything is kind of spread out. Here you have revisited filter that I have kind of adjusted. It's a multi-stage low-pass filter with a little bit of spice, since I added this resonant section that blocks a certain frequency that came up in the FFT, the fast Fourier transforms. As I saw on the boat plot, it was quite high, and it was 80 kilohertz. That's what's coming from the switching, and this basically combats this LC pair. Now there are 8 pins instead of 6 pins. There's the UPDI, which I'm not fairly certain how it's gonna work, although I have done already some research. You have obviously the usual SPI, the buzzer, because I already own a power supply that has a buzzer, and I kind of like it. When I press stuff, it makes a sound. You have also the reset button. That's probably going to be reserved for debugging purposes and nothing else, since it's going to be inside of a metal enclosure. I don't know if I have mentioned, because the first episode was recorded with my Polish voiceover, so I don't think if I'm missing some stuff that may confuse people watching this who only speak in English. So here is the connector that connects the microcontroller and the rest of the board to another board. That's going to be a PCB that contains the display, some buttons, the 7-segment displays, the encoder knob, some multiplexers, and maybe some LEDs. And that's basically it for the change I have made. I have also introduced here a crowbar circuit. It's a protection. It's a circuit relegated to protection. It has basically 2 purposes in my circuit. First of all, it facilitates the OVP, over voltage protection, by basically shorting the power supply if the output voltage is lower than something that it has on the circuit. So basically it protects, like, that's how I understand how any other manufacturers are making this function, is by basically shorting some sort of load if there is some sort of external voltage applied to a circuit that might break it. OCP is very easy to make, because it basically just shuts down power if it reaches the given limit. That's quite trivial. Here you have quite a powerful resistor that pulls the power out of the circuit and throws it into this resistor. And also there is one thing that's quite a niche scenario, but if, for example, you set the power supply to a somewhat high voltage. So for example, like 20 volts, and then you want to power something that's you are changing the settings, and now you want something that only uses 12 volts. So now you have an issue, because those capacitors are loaded to 20 volts, and they are not just going to suddenly lose all their voltage. You cannot plug the 12 volt device, because it will get suddenly a short moment, and yet a dangerous one, when it can just get too high of a voltage. So that's another thing that the crowbar does. It just basically discharges if the new voltage is set to a lower level, it basically discharges these capacitors to a new level. I think this also should work if suddenly the constant current mode is entered, and not the constant voltage, because constant current makes the voltage drop. So that's basically it. There is also a small detail here that what it is basically there is just a diode that will allow me for easier debugging, and that's basically it. I don't know, there most stuff here is self-explanatory. ADC pins are basically, they will just allow for a active readout of voltage and current. So for example, if you are in a constant voltage mode, you don't need to read out the voltage, because you know what the voltage is, because you set it yourself. But you don't know the current, because that's not what you set. The resistance of the output device may change, so that's not something you can set yourself. That's what the receiving device kind of determines. So basically, if you're in a constant current, you know the current because you set it yourself, but you don't know the voltage because it changes as the resistance changes. And that's basically what these two do. This plug-in into the comparator inputs of the TL494, as I mentioned previously, this will need to be verified if this works. Okay, but most of the important stuff doesn't lie on the schematic. It is actually in the PCB. So let me just jump in and show you guys what I have done here. Okay, so now we have the PCB. I don't know what was the state of development when I showed it previously. I think that definitely microcontroller was different. There wasn't a button here, and there were many multiple changes across multiple versions. But basically the gist of it is there is now this connector that allows that just basically is a kind of a information and power bridge between the main board and the display, the frontal panel PCB. That's basically each of those pins serves an important function. Those are new diodes. I even made kind of those special slotted holes. I don't know how the fab will do them, but I hope they do them well. I just want to have kind of a more tight fit when I will be kind of putting them putting the diodes in the slots. The same applies for the I recall those having also slots. I will maybe change that later. Here's the PFC. Here's the shunt for the high voltage, not the low voltage, because there's such immense current that will be going through the low voltage side that there is no, like, it would take an awful lot of surface mount resistors or maybe even through hole ones to do this, so that's not possible. There will be an external shunt that will allow me to control the current passage. Here's the PFC. It is based on IC. This is basically because most of the stuff present here in this circuit was something that I already had available, so I wanted to limit the amount of stuff I have to buy. So that's how it's going to be. As you can see, most of the components are THT, which I decided to do this way because it's just a prototype. There will be probably a release version, a so-called release version that will have most of the components changed to SMD, so it's more compact. Here you have the programming interface, the information plug, and the buzzer, and the multi-segment filter, the output control MOSFET, and as you can see, there are still the rat lines present because it's just impossible. Some traces are impossible to route on this board because there is just too much conflict, and I think some of the traces will just need to be like wired, like made with a physical wire that connects 2 points, which is not a perfect solution, but that will have to do. Here you can see that the footprint was tilted by 45 degrees to allow a better access to the pins itself. Here's the reset button. This is kind of you would probably some of the placement of components may not be obvious why I chose to make this way, but when you realize in what kind of placement and what kind of role they play, you understand why actually I play them in such a confusing way. For example, this is the 3D view of my board, and here you can see the reset button. You can see the 2 potentiometers that regulate the kind of voltage division. They are basically for regulating important voltage dividers that feed voltages into the comparators inside this switching IC. So basically, there is going to where you see this outline, there is gonna be like a large transformer. That's basically the heart of this circuit, and it will have a hole because it's a toroid, so it has a hole, and through this hole you will have a limited amount of access. When the transformer is mounted, you will have a limited amount of, at least I will have, because this is a prototype, so probably only I will have the access to it. So through this hole, the button itself is going to be somewhere here, so you could like stick a screwdriver in there and press it theoretically. Also, those knobs for turning the potentiometer are also accessible when the transformer is mounted. There also is kind of, as you can see, most of the components are quite short in this section. That's because everything below this outline needs to be lower than I think 11 millimeters, because if they were like taller, they would just collide with the plastic structure of the cover of the transformer. So that's kind of another necessity. Those capacitors are actually taller than the 3D model suggests. That's because and so they will need to be actually laid down as the outline here shows, and that will allow me to use a tall capacitor while not colliding with the plastic kind of underside. And that's basically it. I explained, I don't know if I should do this, but I explained in the previous video basically what's the design, like how it's designed, this switching mode power supply. It's basically it's a full bridge resonant. I'm not sure if it's actually resonant, but I think it's resonant, full bridge resonant power supply. I might actually show my simulation in LT Spice. Here's the simplified circuit. I maybe I will be even able to run it, and maybe there will be some interesting results that I will be able to show you. As you can see, this is not the usual way those power supplies are built. This is kind of, I think it's called an LLC, full bridge topology, and it has not in parallel, it has in series a capacitor that makes this circuit resonant and makes it somewhat more efficient than if there was just a short here. I could try to run it and show you, but the simulation has quite a short time step, so it takes a lot of time. As you can see, or maybe not see, the simulation is only 0.1% done, so it's not something that I don't know I could show you right now. But I mean, this circuit works. I have simulated it multiple times with slight changes to see what's the optimal values for these components, and I think my solution is quite close to perfection. It's obviously not like the perfection because it's impossible due to multiple resistances, but I like it. I'm very, very proud of what I made, and I'm happy. So that's the simplified circuit that allowed me for efficiency. It allowed me to figure out the configuration that maximizes efficiency of this circuit.